Welcome to this video presentation by the postgraduate student whose poster it represents. We will miss the bustling crowds around the posters at the All Energy Conference this year, but we hope you enjoyed this online version that we have created. Before the presentation starts, I would like to acknowledge the support of our generous sponsors. Without this support, the competition could not proceed and the winning entrants would not receive a financial award. Our platinum sponsor is the Victorian Government through the Department of Environment, Land, Water and Planning. Its brands include Victorian Energy Compare, Victorian Energy Saver, Victorian Energy Upgrade Program, Energy Scorecard and Energy for Business. Their contact details are on the slide. Monash University's Monash Energy Institute is one of our silver sponsors. With over 170 staff involved, the Institute has a vision to bring people together to solve global energy problems. The Monash student posters in this competition represent some of that work. Baywa Renewable Energy is another silver sponsor. Baywa develops both wind and solar projects in Australia as part of a global energy portfolio. Baywa staff have also supported our AIE events in the past, including our Young Energy Professionals Speed Networking events. Our final silver sponsor is the University of Melbourne's Melbourne Energy Institute. Many of you will have attended their regular forums that keep the energy community and public up to date on technical and policy energy matters, and the University of Melbourne posters in this competition reflect some of that work. Seed Advisory is our bronze sponsor, and this small but well-recognised energy consultancy covers both the technical and regulatory fields. Seed Advisory has been a regular supporter of the AIE and a presenter at our events. Lastly, we thank All Energy for hosting our live poster events over the last decade, and we look forward to doing this again post-COVID. These last slides show you our poster winners in the last competition. And I now hand you over to the poster presentation. Thank you.
Hello everyone, this is Saheli Biswas from Chemical Engineering Department of Monash University, and my poster topic is Energy Efficiency Comparison of Carbon Dioxide Valorization to Methane to Different Electrolytic Routes. One of the biggest challenges over the past few decades has been the huge greenhouse gas emissions. For example, in 2018 and 2019, the overall carbon dioxide emission from energy sector was 33 gigatons, which was 1.7% higher than the previous year. So efforts are being constantly made in different areas to reduce the carbon dioxide emissions. Another pathway being parallelly explored is the valorization of atmospheric carbon dioxide, which means directly capturing carbon dioxide from the air and converting it to fuels and chemicals through zero-emission processes like electrolysis. Now, methane is one such highly valuable fuel since it is a major component of natural gas and can be essentially used for all those purposes where natural gas is being presently used. Now, the most widely studied route of methane synthesis is the production of hydrogen in an electrolyzer and then reaction of that hydrogen with carbon dioxide in a separate reactor to produce methane. So that's a two-step process. However, a comparatively early stage technology that allows one-step direct conversion of atmospheric carbon dioxide to methane is based on solid oxide electrolysis. Now, like most other electrolyzers, solid oxide electrolyzers also have three major components: cathode, anode, and electrolyte. Now, the cathode splits steam or carbon dioxide or a mixture of both into hydrogen and carbon monoxide along with the production of oxide ions. And these oxide ions then travel through the electrolyte to the anode where they evolve as pure oxygen. Now, solid oxide electrolyzers have four major advantages. First of all, they have high cell efficiency as compared to other state-of-the-art electrolyzers like alkaline electrolyzer, that is AEL, or proton exchange membrane electrolyzer, that is PEM. Secondly, it can be coupled with renewable energy sources to acquire the electrical energy required to drive the process. Thirdly, the cell thermodynamics brings down the operating cost because the electrical energy needed to drive the electrolyzer can be partly replaced with heat energy, and heat can come from either solar thermal or industrial waste heat. And the last and most important advantage is that it is the only type of electrolyzer that allows electrolysis of carbon dioxide. And this property can be harnessed for the in situ synthesis of methane within the electrolyzer itself via simultaneous electrolysis of steam and air captured carbon dioxide with proper choice of electrocatalyst to support the methanation reactions. So one of the primary objectives of our research was to determine if this one-step methane synthesis in solid oxide electrolyzer is more energy efficient as compared to other two-step electrolytic routes of methane synthesis. So we considered 4 different electrolytic routes of carbon dioxide valorization to methane. In route 1, hydrogen produced in AIE or PEM electrolyzer reacted with carbon dioxide in a separate reactor. In route 2, hydrogen produced in solid oxide electrolyzer reacted with carbon dioxide in a separate reactor. In route 3, syngas, that is mixture of hydrogen and carbon monoxide, was produced in solid oxide electrolyzer, and this syngas then underwent methanation in a separate reactor. So essentially these 3 routes are 2-step processes, and route 4 was the one-step in situ synthesis of methane in solid oxide electrolyzer via co-electrolysis of steam and carbon dioxide. And for all these 4 routes, we calculated 3 parameters: the overall energy demand for the process, the energy efficiency, and round-trip energy efficiency in case that methane is converted back to hydrogen via steam reforming. And we found that the electrolytic routes employing solid oxide electrolyzer, that is routes 2, 3, and 4, were more energy efficient as compared to AIE or PEM, that is route 1. And in situ methane synthesis, that is route 4, was more energy efficient, and in fact the highest energy efficient of 89%. It gave the highest round-trip energy efficiency of 62% and required the least energy of around 26 megawatt hour per ton of methane. So based on all these observations, we can conclude that in situ synthesis of methane in solid oxide electrolyzer via co-electrolysis of steam and carbon dioxide is an energy efficient, zero emission and sustainable way of atmospheric carbon dioxide recycling. However, the major challenge here is the technology nascency, and we need to develop cathode materials that can improve the reaction kinetics and product selectivity. So such materials should essentially have 4 critical features: good electrical conductivity, good phase compatibility with the electrolyte, good mechanical strength, and most importantly, good catalytic activity to support both co-electrolysis and methanation reactions taking place simultaneously. And this is the area that we are presently working on. Thank you for your attention.